Alright, so let's continue to the next topic, which is the mass transfer coefficients for design of packed towers. So I divided this topic into two parts. So this is part one of the topic. So at the end of this first part, you should be able to do these three things: distinguish the operation and features of straight tower and packed tower, explain the theory of interface mass transfer for absorption and stripping, then derive the equations to determine the height of a packed tower using film and overall mass transfer coefficient based on gas phase and liquid phase driving force. So if previously in distillation, we have tried to design trade towers, and also in previous topic, the design of absorption tower is still using tray or plate towers. But an alternative to absorption column is to use packed towers instead of tray towers. The idea is if you have the tray tower, the absorption tower, instead of having trays inside the tower, you fill in the column with solid packing, right? These are solid packing. So the packing is shaped to provide liquid and vapor mass transfer area. So here in this case, the idea is you provide gas inlet, liquid inlet, and then you ensure the complete mixing of gas and liquid phases and the mass transfer between the solute into the liquid phase using the packing. So in packed tower, there is no discrete or identifiable stages because technically there is no stage. It's just a packing of something. So liquid and vapor are continuously contacted inside the packing, and the mass exchange that brings the two phases to equilibrium. So here the driving force is not equilibrium. Right, so let's have a look at some differences between the mass transfer operations in packed tower and trade tower. Okay, in terms of surface area for mass transfer, for trade tower, the surface area for mass transfer is provided by the bubble and liquid interface, but in packed tower is provided by surface area of the packing. In terms of equilibrium, vapor and liquid phases leaving the stage are assumed to be in equilibrium in a tray tower. Okay, but because it cannot reach equilibrium in the real world, so the non-equilibrium is accounted for with the stage efficiency. So, and the operating points are given by set of xn and yn plus 1. Then, but in packing tower, vapor and liquid are not in equilibrium. They are not at equilibrium inside the packing. It is the non-equilibrium that provides the force for mass transfer. Okay. Okay, let's have a look. When do you choose to use tray tower or packed tower? So you can have a look here. What are the advantages of tray tower and packed tower respectively? So basically, we use tray tower if you have a higher vapor flow rate and i.e. larger diameter, and if you have more number of theoretical stages, then better use tray tower because of redistribution issue. You want to maximize the mass transfer, and then tray tower are also better for large fluctuation of temperature and more suitable for highly exothermic endothermic operation because it's easier to feed heat transfer surface, and better use tray tower for highly fouling conditions. Okay, so because if this is in case if the tower provides for some access for cleaning. But however, some advantages of packed tower is you have lower pressure drop for the gas phase. For example, if you want to use vacuum distillation, lower capital cost, as we mentioned in the design of distillation column topic. If the diameter is less than 0.6 meter, it's better to use packed tower. And also the packing can be made of corrosion resistant materials or such as ceramic, so you can choose the type of packing based on the fluid that passes through the tower. Alright, so I'm sure that you may have may have heard of the two film theory and overall mass transfer coefficient when you learned mass transfer previously. So basically in two film theory you have gas phase and liquid phase. The mass transfer, if absorption, you have the solute in the gas phase, you want to transfer the solute into the liquid phase. So between the gas and liquid phase, there's an interface here. So you have a bulk gas composition Y, or if in terms of partial pressure is P, and then however nearing the interface you have the Yi or Ti at concentration at the interface, and then as mass transfer occurs, then the concentration of I, the solute in the liquid phase, is Xi or Ci at the interface, and then we will go to the bulk phase composition of the solute in the liquid phase. So the idea here is to film theory, resistance to the overall mass transfer is viewed as combined resistance of liquid and gas film at the interface, because anything in life actually is, I think I've mentioned this to you, I don't remember, I've mentioned this too many times, rate of whatever, right? Rate of anything is equal to driving force divided by resistance. So in mass transfer for absorption, the driving force here is the difference in concentration, and the resistance is this resistance in the liquid and gas films at the interface. Okay. If you have, for example, heat transfer, the rate is, the driving force would be the difference in temperature, and the resistance is taken into account as the, what do you call it, heat transfer coefficient, right? And then also in current situation, the rate of you studying anything equals to your driving force divided by your resistance. It's a lot of resistance learning from home. The driving force could be your motivation, or however that motivation may come in various forms. But there's a lot of resistance to study at home, a lot of distractions. So that's why your rate of studying is different if you were in campus versus when you were at home. Or maybe it may not be applicable to all, but at least it is applicable to me. Okay, let's have a look at the concentration profiles in the interface mass transfer. So let's say your flux of A is your solute which you want to transfer from the gas phase into the liquid phase. So this is the direction of your flux on A. So you have the, let's assume solute A is diffusing from the bulk gas phase G to the liquid phase L. So this is the bulk gas phase G, and this is the liquid phase L. So it must pass through the phase G through the interface. Your interface is this one, okay? So a concentration gradient must exist to cause this mass transfer, because this will give the concentration gradient would be the driving force, and the resistance would be the resistance at the interface between the gas and liquid film. So let's put YAG as the average or bulk concentration of A in the gas phase. So this YAG is bulk concentration of A in the gas phase, and XAL would be the bulk concentration of A in the liquid phase. Everything here we are talking in terms of a mole fraction. So YAG, as it transfers from the bulk phase to the interface, it will decrease to YAI, and then the liquid concentration starts at the XAI, and then it will decrease to XAL. Okay. Okay, right. There, at the interface, we would assume that there is no resistance to mass transfer. Thus, the between the YAI and the XAI, we can use equilibrium relationship. So, for example, with analytical relation, you can use Henry's law. Or if you don't have an analytical expression to express the relation between YAI and XAI, then you must have some table of YAI and XAI. Thus, you will have some equilibrium data to give the relationship between YAI and XAI. Okay, let's have a look at the mass transfer using film mass transfer coefficient and interface concentration. So let's say you have your bulk phase concentration YAG, and then this is your bulk gas phase concentration. Then you have the interface between the gas and liquid phase. And as the concentration profile decreases. Here would be your YAI, and then this is XA in the interface, and then it will go through XAL at the bulk liquid concentration. Okay, so here let's have point P as the bulk phase composition YAG and XAL. So if you put these coordinates here, YAG and XAL, you have point P, the XAL and YAG. And the point M is the interface concentration YAI and XAI. So here XAI and YAI you put on the X and Y diagram. So we mentioned previously that YAI and XAI can be related using the equilibrium relation. So if you have an equilibrium line drawn, then if you plot XAI, it will fall on the line, and then it will have this YAI here as the Y coordinate. So this would be your point M. Okay, so for a solute A diffusing from the gas liquid to B, from gas to liquid and B in equimolar quantification. So you should know what is equimolar quantification from now. I mean by now from mass transfer. So here we are saying that there is transfer from gas to liquid, and there would be transfer from liquid to gas also because of equimolar quantification. So you can so this would be the direction of your flux NA. So you can write down the flux of NA equals to KY prime and YAG minus YAI in terms of gas phase, and in terms of liquid phase concentration it would be KX prime and XAI minus XAL. Okay, the higher concentration minus the lower concentration, because this would be the driving force. So what are KY and KX prime? They are just the mass transfer coefficient, liquid film mass transfer coefficient in terms of gas phase and in terms of liquid phase. You may have seen different subscripts such as Kg or Kl, but it just means the same, either it's in gas phase or in liquid phase. So if you have a look at the diagram here, so if you want to find out the slope of line PM, it would be the delta Y divided by delta X. So the delta Y, so slope of line PM, slope equals to delta Y over delta X equals to YAG minus YAI divided by delta X is XAL minus XAI. So when you rearrange this equation, you would get KY over minus KX. So that's why it says here the slope of the line PM is, terbalik. If you rearrange the equation from this one, you will get Kx over Ky, negative sign because instead of XAI minus XAL, here is XAL minus XAI. Okay, so that's why it says here the slope of the line PM is minus Kx over Ky prime. Okay, what about just now we talked about the equimolar counter-diffusion. What about the mass transfer when there is diffusion of A through stagnant or non-diffusing B? So A transfers from the gas phase to the liquid phase, but the liquid phase B does not transfer through the gas phase, does not transfer to the gas phase. So this is the case in most of our absorption assumption. Okay, diffusion of A through stagnant or non-diffusing B. So the same case as before, you have your flux and A this direction. So you have your YAG, and then at the interface you have here YAI, then you have XAI, and then it reduces to XAL. So if you just plot the points on the graph of X and Y here, so if you have at YAG and XAL, you have this point P, and point M is at the interface concentration, same thing. So, but in this case here, for solute A diffusing through a stagnant gas and through a stagnant liquid, only the solute A transfer, but the gas and liquid does not transfer through each other. So you write down your flux here, and A equals to Ky times YAG minus YAI in terms of gas phase, and in terms of liquid phase is Kx times XAI minus XAL. But here, the Ky equals to Ky prime divided by the log mean average of the 1 minus YA at the interface. And also same thing for the liquid phase coefficient for mass transfer. So here, this is how you calculate the 1 minus YA at the interface log mean. So I'm sure you have seen this log mean difference before in at least in heat transfer, the temperature T1 minus T2, the log of T1 minus T2 and so on. Okay, so just to say that the difference here is if you have a diffusion of A through stagnant gas and stagnant liquid, this is what the equation that you should be using. Okay, like previously we have done for the equimolar contour diffusion for the point P and point M. So for the line PM, if you want to calculate the slope of the point PM, you would calculate the delta Y divided by the delta X. So the delta Y here is YAG divided YAG minus YAI, and the delta X is XAL minus XAI. And also previously you have seen that for diffusion of A through stagnant or non-diffusing B is NA equals to this, and in terms of gas phase, and NA also, the flux of A equals to this in terms of the liquid phase. So you see the similar terms here, YAG minus YAI and XAI minus XAL. So here if you rearrange to be like this, you shall get something like this with the negative sign in front because of this XAL minus XAI instead of XAI minus XAL. So then the slope of the line PM is given by the left-hand side of the equation above. So when A is diffusing through stagnant B and the solutions are dilute, when the solutions are dilute, i.e. the concentration is less than 20%, then 1 minus Y8, these terms are close to 1, then you would also assume the slope of the line PM would be just the ratio of this without the log mean term because it's close to 1. This is only applicable when the solutions are dilute. Okay, so now we will talk about, instead of using film mass transfer coefficient, we will instead use overall mass transfer coefficient and the driving force. Because the film mass transfer coefficients, previously we only used the film mass transfer coefficient, the small k for y, x, prime or not prime, depending on whether it's equimolar contour diffusion or diffusion of A through stagnant gas or liquid. Okay. But however, the film mass transfer coefficient are difficult to measure experimentally. So instead of using film mass transfer coefficient, overall mass transfer coefficients will be measured based on the gas or liquid phase. This is analogous to heat transfer, where you use overall heat transfer coefficient, overall heat transfer coefficient instead of using the film coefficient because it's easier to measure. So in terms of overall mass transfer coefficient, the flux NA is defined as, in terms of gas phase, NA equals to capital K Y prime times YAG minus YA star. So here you don't use the interface concentration anymore. Okay, just to recap, YAG, and then you have the interface concentration here, YAI. So you don't use the I concentration anymore, but instead you use star. So what are the star equation, the notation? So YA star would be the value that would be in equilibrium with XAL. So here we want to talk about things that we can measure. So we want to talk about things that we can measure. At the interface, it's difficult to actually measure the concentration of gas and liquid phase at the interface. It's nearly impossible. Very difficult. Maybe it's possible, but it's very difficult. But it's easier for you to measure YAG and XAL, the bulk phase concentration. And also, we want to use the equilibrium value so that it's easier to measure. So here, if you can measure XAL, then you can estimate, you can get YA star. Then YA star would be the value that will be in equilibrium with XAL. So if you have this equilibrium line on the X and Y axis, so if you know XAL and YAG, because this one are the bulk gas phase concentration, so if you plot here, then the value of Y that will be in equilibrium with XAL is the YA star. Same thing for liquid phase concentration. So in terms of liquid phase concentration, the flux NA is given by this equation, Kx times, here instead of XAI, you use XA star minus XAL. XAL is still maintained as the smallest concentration here, so XA star replaces XAI. So here XA star would be the value that would be in equilibrium with YAG, because YAG is measurable. So if you know YAG, then you bring it to the equilibrium line. So the value of X that will be in equilibrium with YAG is the XA star. So these are the terms that you use if you want to use the overall mass transfer coefficient instead of the film mass transfer coefficient. So you don't use the YAI and XAI, you use YA star and XA star. Okay, let's have a look how to use the overall mass transfer coefficients and driving forces for equimolar counter diffusion and or diffusion in dilute solution, because as we mentioned previously, if we have dilute solution, then it can be approximated as equal to equimolar counter diffusion expressions, because 1 minus YAIM and 1 minus XAIM would be almost equal to 1. Okay, so let's see the expression for equimolar counter diffusion, or when the solution is dilute, the Na equals to Ky times YAG minus YAI in the gas phase term and equal to Kx times XAI minus XAL. So if you have this figure, look at this graph here. Okay, so we say that if you know YAG and XAL, then you can get the YA star and XA star from the equilibrium line. Okay, okay. So from the figure here, you can see that YAG minus YA star, okay, this distance here is equal to YAG minus YAI, the distance here, plus the distance here, YAI minus YA star. Okay, between the points point E is this, and point M is at the interface, okay, then we have the slope M star. So this is the line if you connect the point E and M. So the slope M prime can be given by, okay, the slope M prime, if you have this, then the slope would be, this would be your delta Y, this would be your delta X. So delta Y here is YAI minus YA star, okay, and your delta, this is your delta Y, and then your delta X is XAI minus XAL. Okay, so this is your M prime, then you have YAI minus YA star equals to M prime times XAI minus XAL, just rearranging that equation. So if you put this into the equation here, then you will have YAG minus YAI equal to YAG minus YA, YAG minus YA star equal to YAG minus YAI, plus in this case YAI minus YA star, but here you substitute this term into here and then you get this. Okay, and also NA equals to KY YAG minus YAI equals to KX XAI minus XAL. Okay, from this equation here, substitute the overall mass transfer equation, and also in terms of overall mass transfer equation, NA equals to KY YAG minus YA star. Okay, from here you get YAG minus YAI equals to NA over KY prime, XAI minus XAL equals to NA over KX prime, and YAG minus YA star equals to NA over capital K Y prime. Then you put this everything here into this. So YAG minus YA star equals to NA over K Y equal to YAG over Y minus YAI is NA over KY plus M prime times NA over, yeah. So you substitute already with overall mass transfer equation NA and cancelling out the term NA, so cancel, cancel, cancel. Then you shall get the 1 over ky equals to 1 over small ky plus m over kx prime. So this would be your this one. Okay, so what is the significance of the expression that we have just derived previously, this one? What does it mean? So it just means that it is the total resistance. So this one is the term total resistance based on gas driving force, overall gas driving force. And this term here is the resistance of gas film. And this term here is the resistance of liquid film. Film, liquid, and gas film. And this one is overall. Okay, so you can know what would be the controlling phase for your mass transfer, either which one has more resistance, in the liquid film or in the gas film. Then that would contribute to the overall resistance. But you can do the same thing, similar derivation for the liquid phase driving force, because previously we are using during the derivation based on gas phase driving force. But if using liquid phase driving force, especially for stripping, then you can start with the distance between these XA and XAL. The distance between XA star and XAL equals to the distance here plus the distance here, right? Distance here plus distance here. And then based on liquid phase, this is your 1 point in the XA star and YAG. And then at the interface is XAI and YAI. So if you connect the two points together, you get this line DM. And then this would give you the slope equals to M star, M double prime. So that's why it says the slope M double prime is your delta y divided by delta x. So here is your delta y and then here is your delta x. And then you proceed as before, replace with the NA, the flux, then you can get this expression here. This expression here. Then what does it mean? I would advise you to try to derive this on your own, because I've shown you how to derive for the gas phase, so now you derive for the liquid phase. Okay, so here the total resistance based on the liquid phase driving force overall, and here would give you the resistance of gas film, and this one is the resistance of liquid film. But it's slightly different from the one that we have in the gas phase, because now we are using the liquid phase driving force. So this would give us a comparison for the overall mass transfer coefficient and driving forces in the liquid and gas phase. So from this expression here, so if M prime is small, but the equilibrium curve is almost horizontal. So you can imagine if M is very small, then the gradient is very small, then your equilibrium curve may look like this. Okay, like it's very flat. If it's a straight line, then it should be a straight line if it's y equals to mx. So here, a small value of ya in the gas phase would give the large value of xa. How do you visualize that? If you have a very small ya, then you would get very large xa. I mean, if it's steep, this small ya would give you small xa. Okay, large ya will give you large xa. But if it's very flat like this, then small ya would give you very large xa. That's what it means. And then the gas solute A is then very soluble in the liquid phase. And then the term here is very small because it's like no resistance in the liquid phase because the gas is very soluble in the liquid phase. Then because this term is very small, it becomes negligible. So 1 over capital K y prime would be almost equals to 1 over small ky prime, i.e. the major resistance is in the gas phase, the gas film. So in other words, the gas phase is controlling the mass transfer, i.e. normally this would be the case for absorption. The gas phase is controlling the mass transfer. Okay, what about this term here? Okay, so here if m double prime is very large, the gas solute A is then very insoluble in the liquid phase. So the term here would be very small because this is large. Okay, 1 over something large would give you very small term. Then 1 over capital Kx prime would be almost equal to 1 over small kx prime, i.e. the major resistance is in the liquid phase. So in other words, liquid phase is controlling the mass transfer. So this is normally the case for stripping. Okay, just now we talked about equimolar counter diffusion or very dilute solution, dilute mixture. But if the mixture is not dilute, then we cannot assume the same case. So in most cases for absorption is diffusion of A to stagnant or non-diffusing B. And if the solution is not dilute, you have to use this equation, these expressions. So for the case of solute A diffusing through non-diffusing B, as you have seen previously, this could be the equation. And we name the equation here as 2.1 because of this 2 here, and this is the first equation that appears. And then if you look at this graph here, YAG minus YA star, so the same thing also, the distance between YAG and YA star is the distance between this plus the distance between this. And replacing this with the m star here, as we have done before. We are not repeating the derivation. And also now we are talking about in terms of the overall mass transfer coefficient. So let's define the equation using overall coefficients. So we don't use the A sub I anymore in the gas and liquid phases. So NA equals to, here because of the overall we use capital K, and instead of YAI use YA star the log mean. So YAG minus YA star, these are in terms of gas phase. And in terms of liquid phase driving force, 1 minus XA star M, XA star minus XAL. So here, 1 minus YA star M is given by this definition here. So if you have 1 minus XA, then you just replace the terms YA with XA lah, and YAG with XAL. Okay, so the bracketed items here are normally simplified, defined as this one. Okay, simplified lah, meaning instead of using this bulk expression, you just put KY and KX without the prime. So meaning whenever there is without the prime, you have to take into account, it's already taken into account the log mean difference in the concentration respectively in the gas and liquid phases. So here you have 1, 2, 3 equations. So if you substitute equations 2.1 and 2.3 into the equations 2.2, you can try doing the derivation yourself, then you will end up with this expression here. Okay, so how are we going to use this expression? So just now we talked about the gas in terms of gas phase derivation. So same thing for absorption, stripping. So if you talk about in terms of Kx, in terms of liquid phase, then you derive this from this would be your new equation 2.1, 2.2, and 2.3. So you substitute 2.3 and 2.2 into 2.1 into 2.2, then you get this. You can do your own derivation. You can pause the video and do the derivation. Where now the term is this one. So the relations here derived here are applicable for any two-phase system. Okay, not necessarily gas and liquid. Just one phase stands for one variable. Y stands for one phase and X for the other phase. For example, you can use this in liquid extraction also later. Okay, it's just that now the concept is that you have to know how to express the transfer of solute from one phase to another. Okay, so from bulk gas phase to the bulk liquid phase, and the relation with the equilibrium concentration, and also the relation with the interface concentration. That is the whole point of this half an hour derivation of various expressions. It's just for you to know where the equations are coming from so that we can use it to design our pack tower later, to determine the height of our pack tower. Okay, so let's talk about the film and overall mass transfer coefficient in pack tower. So actually it is very difficult to measure experimentally the interfacial area between the phases, liquid and gas. Very difficult. I mean, you can imagine if you have gas and liquid inside the column, how are you going to measure the interfacial area between the gas and liquid phases? You can't really see the barrier between the gas and liquid phase. Similarly, it is difficult to measure the coefficients, either interfacial film coefficient or the overall coefficient. Although we say that overall coefficients would be preferable to use compared to film coefficient, but still it is quite difficult to measure. So usually the experimental measurement in pack tower, instead of the kx and ky, the overall mass transfer coefficient, it will yield the volumetric mass transfer coefficient. It combines the interfacial area and mass transfer coefficient. So instead of kx and ky, you would have kya times, you would have both. I mean the combination between the mass transfer coefficient and the interfacial area, because that would be easier to measure, the volumetric mass transfer. So let's define A, small a here, as the interfacial area in meters squared per meter cube volume of packed section. And the volume of packing in the height tower dz is S dz. So S, it would be the surface area, cross-sectional area. So dA is equal to A times S dz. Okay, just to check on the dimensional consistency. So unit of A is meter squared per meter cube volume. Interfacial area in meter squared per meter cube volume. S, the unit of S is meter squared. The unit of dz is meter. And the unit of A is meter squared. So A is the interfacial area between the phase. So it's difficult to measure. So you can measure this, and this. So the unit for volumetric film and overall mass transfer coefficient are defined as Kxa equal to the unit of Kxa, Kya, and so on, kilomole per second per meter cube of packing times mole fraction. So you have to be careful here in terms of kilomole, mole fraction. If in terms of kilogram, then mass fraction. You have to be consistent with the unit that you use. Okay, so let's have a look at this column, pack column. So our notations are the same. So the bottom of column is number 1, the top of the column is number 2. So we will use this for the next derivation. We will proceed to the design method for pack tower. So you have seen this column. So it's point number 2, point number 1. So you have seen this operating line. So this is just input equals to output. In terms of the control volume, here is the dashed box. Okay, for a differential height of the tower dz here, the moles of A leaving B is equal to the moles of A entering L. Okay, just mass balance. This amount of solute leaving the gas phase equals to the amount of solute entering the liquid phase. So you have the differential amount d times dy equals to d times Lx. These are all in terms of the solute A. Okay, what V, L, and X are just, X and Y are just mole fraction. So the kilomole of A transferred from dV equals to dLx must also equal to the kilomole of A transferred from the mass transfer equation, the flux. Okay, the flux. So Na must be equal to Na dA equal to dVy equal to dLx. Okay, so let's derive the equation to determine the height of a packed tower Z. The height here is Z because the dz differential height. Okay, let's do the derivation based on the gas phase driving force. So you have seen this equation before for the diffusion of solute A through stagnant B. Okay, you have seen this equation before. So multiply this equation with dA equals to AS dz. So that's why right hand side multiply with dA, so you have NA dA. And the right hand side here multiply with AS dz, so you get these terms. So NAdA is the kilomole of A transferred in the height dz in meter. So then in terms of gas phase, you use the dVy. Okay. So previously you know NAdA equals to dVy equals to dLx. But if we just use the gas phase driving force, so we just use the Vy. So dVy equals to NAdA, and using the YAG for the bulk gas phase concentration of A, so you just replace the Y with YAG, because we just want to make sure consistency lah. Okay, Y is actually in terms of solute A. So here you replace with this NA, I mean you replace the Y with YAG, and then NA is equal to this equation. So you substitute NA here and then S dz, and also you have A suddenly here because of this. Okay, and here also you have seen the KYA. Next, so if you recall that the inert gas phase concentration V prime equals to V1 minus Y, right? If 1, then it's 1. If 2, then it's 2. Okay, but okay, whatever the subscript is, V times 1 minus YAG, or you can also rearrange here to get V equals to V prime over 1 minus YAG. So the same thing, so you put this inside this equation of D times VYAG. So you substitute V here with this term, and then you get this, and then you differentiate with respect to YAG. So I'm sure you know how to differentiate it by now. You can do it step by step, and finally you get this term. Okay, V times dYAG over 1 minus YAG. Then this one is your dVYAG already. So you substitute this, it equals to this. Okay, follow the previous slide also. Then you just drop the subscript subscript A and G in all of the equation here. So you just end up with V dy 1 minus y equals to everything here. Then your goal is to find z. Okay, your goal is to find z. So you rearrange the equation, you put dz at the left hand side, and you integrate from 0 to z. So here you visualize, this is your power, then here is your y1, here is your y2, here is your x2, here is your x1, but the x's here, x1, x2 here does not matter, because we are talking about in terms of the gas phase driving force. So here in this case, if you integrate from y2 to y1, then your 0 is here and your z is here. So integrate from 0 to z equals to z. Then you integrate, if you rearrange, you will end up with this equation, this expression. Then you should know what is y1 and y2. And then if you know y1 and y2 and you know the v, then you get the z. Because your goal here is to use the mass transfer equation to get the height of the packed tower. You repeat the derivation now using the liquid phase film coefficient, starting from the expression for Na in terms of the liquid phase, uh, and then you follow similar step, then you will end up with similar equation, but now in terms of liquid phase. So instead of D, you have here L, and instead of the Y, you have here dx, and instead of y1 and y2, you have x2 and x1, and yeah, everything in terms of liquid phase. Yeah, so this is in terms of liquid phase film coefficient. We also have in terms of overall coefficient for both gas phase and liquid phase. So you can continue, when you can try to repeat the derivation 4 times. One is gas phase film coefficient, and then liquid phase film coefficient, and then gas phase overall coefficient, and then liquid phase overall coefficient. So you will end up with 4 equations which can be used to calculate the height of the packed tower. So these are the equations that is very important to you to calculate the height of a packed tower. But you just have to make sure you know what are the equations based on. So if you see the interface here, I sub I here, meaning it is based on the film coefficient, either gas phase or liquid phase. But if you see the terms star here, then it's based on overall coefficient, either for gas phase for y's on these, or the liquid phase for the L and the X. Okay, so you have 4 design equation to determine the height of a packed tower. So that's all for part 1. Then we will continue for part 2. We will see some example how you can use all these equations to actually calculate the height of a packed tower.